Imagine something so bright, it outshines an entire galaxy. Something so distant, its light has been traveling for billions of years just to reach your eyes. And at its heart lies one of the most terrifying objects in the universe, a supermassive black hole. This is a quasar. At first glance, it might look like just another tiny point of light in the night sky. But in reality, it's one of the most powerful and extreme objects in the entire universe. A quasar is not a star. It's not even a single object you can point to. It's the blazing heart of a distant galaxy, where a supermassive black hole is actively feeding, devouring enormous amounts of gas and even entire stars. And as this matter spirals inward, something extraordinary happens. It doesn't fall straight in. Instead, it forms a rapidly spinning disk called an accretion disk, where particles collide, compress, and heat up to millions of degrees. This process releases an unimaginable amount of energy, so much energy, in fact, that a single quasar can outshine an entire galaxy containing billions of stars. Think about that for a moment. Billions of stars, all outshone by a region no larger than our solar system. That's the power of a quasar. But the black hole itself remains completely dark. We never actually see it. What we see is the chaos around it. The glowing disk, the violent motion of matter, the intense radiation blasting outward into space. And in some cases, from the poles of this spinning disk, gigantic beams of energy erupt outward, traveling at nearly the speed of light. These are called relativistic jets, and they can stretch across thousands, even millions of light years. Imagine a beam so powerful that it punches through the entire galaxy and keeps going. Now here's where things get even more fascinating. Most quasars are incredibly far away from us. So far, in fact, that the light we see from them today began its journey billions of years ago. When you look at a quasar, you're not just looking across space. You're looking back in time. Back to an era when the universe was young, when galaxies were still forming, and supermassive black holes were growing rapidly, feeding on everything around them. In a way, quasars are like ancient cosmic lighthouses, telling us the story of how the universe evolved. But here's the unsettling truth. If a quasar existed anywhere near our solar system, life on Earth wouldn't stand a chance. The radiation alone would be enough to strip away our atmosphere and sterilize the planet completely. Fortunately for us, the nearest quasars are billions of light years away. And today, most galaxies, including our own Milky Way, are relatively quiet. At the center of our galaxy lies a supermassive black hole. But it's mostly dormant, not actively feeding like a quasar. Which means, what we're witnessing when we observe quasars is not the present state of the universe, but a glimpse into its wild and violent past. A time when darkness didn't dominate the cosmos. Light did. So, what exactly is a quasar? To understand this, we need to rethink what we're actually looking at. A quasar is not a star, even though early astronomers thought it was. When scientists first detected these objects in the 1960s using radio telescopes, they appeared as tiny, star-like points of light. That's why they were called quasi-stellar objects, or simply quasars. But as observations improved, it became clear that these objects were anything but ordinary. They were unbelievably distant, far beyond our own galaxy. And yet, they were shining with an intensity that made no sense for something so small. Eventually, astronomers realized the truth. A quasar is the extremely bright core of a distant galaxy, what scientists call an active galactic nucleus. At the center of almost every galaxy lies a supermassive black hole. Most of them are quiet, but in some galaxies, that black hole is actively feeding, pulling in vast amounts of matter. And when that happens, the galaxy doesn't just glow, it blazes. The core becomes so bright that it completely outshines the rest of the galaxy around. Imagine looking at a city from space at night and seeing a single building shining brighter than the entire city combined. That's what a quasar is like. It's not the whole galaxy we see, just its intensely active heart. And the energy released from this tiny central region can be thousands of times greater than the total energy output of the Milky Way. But here's the key idea. A quasar only exists when the black hole is actively consuming matter. Once the fuel runs out, the quasar fades, and the galaxy returns to a quieter state.
Which means, quasars are not permanent objects. They are phases, brief, violent episodes in the life of a galaxy. And what we're seeing is that phase at its absolute peak. At the heart of every quasar lies the true engine behind its immense power, a supermassive black hole. These are not ordinary black holes. They contain millions, sometimes even billions, of times the mass of our Sun, and their gravity is almost impossible to comprehend. Anything that comes too close, gas, dust, even entire stars, gets pulled inward by this overwhelming force. But here's something surprising. Matter doesn't just fall straight into the black hole. Instead, it begins to spiral faster and faster, forming a rapidly rotating structure known as an accretion disk. Inside this disk, chaos rules. Particles collide violently. Friction builds up. Temperatures rise to millions of degrees. And as this matter heats up, it starts to glow, not just in visible light, but across the entire electromagnetic spectrum, from radio waves to X-rays, and even gamma ray. This is where the incredible brightness of a quasar comes from, not the black hole itself, because the black hole is completely dark, but from the matter, just before it disappears forever. And here's the most mind-blowing part. This process is incredibly efficient. As matter falls inward, a significant portion of its mass is converted directly into energy, far more efficient than nuclear fusion inside stars. Which means, even a relatively small amount of matter can produce an enormous amount of light. It's like turning a handful of fuel into the brightness of billions of suns. As the material moves closer and closer to the center, it reaches a boundary known as the event horizon. Beyond this point, nothing can escape. Not matter, not energy, not even light itself. And once it crosses that boundary, it's gone forever. But just before that final moment, it shines, brighter than anything else in the universe. But to truly understand the power of a quasar, we need to go deeper into the physics governing this extreme environment. Near a supermassive black hole, the laws of classical physics begin to break down, and Einstein's theory of general relativity takes over. Space and time themselves are no longer fixed. They are warped, stretched, and twisted by the immense gravitational force. As matter spirals inward through the accretion disk, it doesn't just accelerate, it approaches relativistic speeds, a significant fraction of the speed of light. At these velocities, even time behaves differently. To an outside observer, processes near the black hole appear to slow down, a phenomenon known as gravitational time. Light escaping from this region also loses energy, shifting toward longer wavelengths, what we call gravitational redshift. This is why the inner regions of the accretion disk emit intense X-rays and high-energy radiation, revealing conditions far beyond anything we can recreate on Earth. And if the black hole is rotating, the effects become even more extreme. The spinning mass drags space-time along with it, a phenomenon known as frame. In this region, called the ergosphere, nothing can remain stationary. Everything is forced to move, carried along by the rotation of space-time itself. These are not just theoretical ideas. They are observed, measured, and fundamental to our understanding of quasars. In essence, a quasar is not just an object. It is a natural laboratory where gravity, energy, and motion interact at the very limits of physics. But not all of this energy remains trapped near the black hole. Some of it escapes in one of the most extraordinary phenomena in the universe. From the poles of the accretion disk, twin beams of energy erupt outward. These are known as relativistic jets. Narrow, focused, and unbelievably powerful, they are launched along the rotational axis of the black hole, guided by intense magnetic fields that twist and coil within the accretion disk. And once these jets are formed, they accelerate particles to velocities extremely close to the speed of light. Not thousands, not millions, but sometimes hundreds of thousands of light-years in length. These jets can extend far beyond the host galaxy itself, piercing through intergalactic. And as they travel, they emit radiation across vast distances. particularly in radio wavelengths, which is how many quasars were first detected. But here's something even more fascinating. If one of these jets happens to be pointed directly toward Earth, the quasar appears even brighter, a phenomenon known as relativistic beaming. In such cases, we classify these objects as blazars. But quasars are not just powerful, they are ancient. Almost all the quasars we observe today lie billions of light years away from Earth. And that distance changes everything, because in astronomy, distance is time. When we observe a quasar located 10 billion light years away, we are not seeing it as it is today, we are seeing it as it was 10 billion years ago. This means quasars are not just objects in space, they are windows into the past, into an era when the universe itself was young, dense, and far more chaotic than it is now. In those early epochs, galaxies were still forming, merging, colliding, and feeding enormous amounts of matter into their central black holes. This is why quasars were far more common in the early universe than they are today. It was a time of rapid growth, when supermassive black holes were building up their mass at And yet, this raises a profound question. How did these black holes grow so massive, so quickly? Some quasars we observe existed less than a billion years after the Big Bang, and already contain black holes, billions of times more massive than our Sun. This challenges our understanding of how structure forms in the universe. Did they grow steadily over time? Or did they form through more exotic processes, such as direct collapse of massive gas clouds? Even today, this remains one of the biggest unsolved questions in modern astrophysics. What we do know is this: quasars played a crucial role in shaping the universe we see today. Their intense radiation influenced the formation of galaxies, regulated star formation, and may even have contributed to reionizing the early universe, a phase that made the cosmos transparent to light. In this sense, quasars are not just remnants of a distant past, they are key to understanding how the universe evolved into it. The story of quasars begins not with theory, but with confusion. In the late 1950s and early 1960s, astronomers using radio telescopes began detecting powerful sources of radio waves in the sky. When they tried to match these signals with visible objects, they found something puzzling. The sources appeared to be faint, star-like points, not galaxies, not nebulae, just. The story of quasars begins not with theory, but with confusion. In the late 1950s and early 1960s, astronomers using radio telescopes began detecting powerful sources of radio waves in the sky. When they tried to match these signals with visible objects, they found something puzzling. The sources appeared to be faint, star-like points, not galaxies, not nebulae, just tiny dots of light. One of the most famous of these objects was 3C273. At first, it seemed unremarkable, but when its light was analyzed in detail, astronomers noticed something extraordinary. Its spectral lines were shifted dramatically toward the red end of the spectrum, a phenomenon known as redshift. This indicated that the object was moving away from us at an enormous velocity, and therefore, it had to be incredibly distant. But if it was that far away, then it must also be unbelievably bright to still be visible from Earth. This realization changed everything. It meant that these star-like objects were not stars at all, but incredibly luminous sources, located at the centers of distant galaxies. The discovery of quasars forced astronomers to rethink the scale and energy of the universe. Over time, more quasars were discovered, each more powerful and distant than the last. Some emitted energy equivalent to trillions of suns. Others revealed jets extending across vast cosmic distances. And gradually, a new picture began to emerge. At the heart of every quasar lies a supermassive black hole. What began as a mystery became one of the strongest pieces of evidence for the existence of black holes on a galactic scale. Today, quasars continue to be studied using the most advanced telescopes ever built, from radio arrays on Earth to powerful space observatories. Each new observation pushes the boundary of what we know and reminds us how much there is still left. So just how powerful is a quasar? The answer is almost beyond comprehension. A single quasar can outshine an entire galaxy, a galaxy containing hundreds of billions of stars. And yet, all of that energy emerges from a region smaller than our solar system. It is intensity, compressed to its absolute limit. The most luminous quasars emit energy equivalent to trillions of suns. Every second, they release more energy than our sun will produce in its entire lifetime. But quasars are not just powerful, they are transformative. Their radiation can heat vast clouds of gas, suppress the birth of new stars, and even drive matter out of entire galaxies. In doing so, they shape the evolution of the universe itself. But here's something important. Quasars are not permanent. They are phases, brief, violent chapters. Once the supermassive black hole exhausts its supply of matter, the brilliance fades, the jets weaken, the radiation diminishes, and the galaxy slowly returns to a quieter state. And this brings us to the present. Today, most galaxies in the universe, including our own, are relatively calm. At the center of the Milky Way lies a supermassive black hole known as Sagittarius A star. It contains millions of times the mass of our Sun, but unlike a quasar, it is largely dormant. It is not actively consuming large amounts of matter, and therefore, it does not shine with the same intensity, which means what we observe when we look at quasars is not the present state of the universe, but a glimpse into its past. A time when galaxies were younger, more chaotic, and far more energetic. In many ways, quasars are like ancient beacons, their light traveling across billions of years just to reach us. They tell a story, not of what the universe is, but of what it once was, and perhaps what it could become again. Because the universe is not static. It evolves, it changes, and somewhere, even now, new quasars may still be forming, hidden in the depths of distant galaxies, waiting to ignite. So the next time you look up at the night sky, remember this: some of those faint points of light are not stars, but echoes of a violent, brilliant past. A past where darkness did not dominate the cosmos, but light, at its most extreme,